Okay, so let's get started. First of all, make sure that you're in the right class. It's Data609 Mathematical Modeling Techniques for Data Analysis, Data Analytics. And then, it used to be, this course used to be a required core course, and then starting from this semester, because of change of the program, we in general we put this as a elective. However, I would say that the methodology that we use here is essential for you to understand whatever methodology that you're learning down the road, such as predictive analytics or data mining or supervised machines. Here really, or machine learning, here really serves as an introduction for or foundation for some of the methodology that you're going to learn down the road. Okay, and then we have multiple prerequisite, including data 600, data 605, data 606. Assume that you should have either already completed this prerequisite or you are trying to take them this semester. Okay, and then what we are trying to explain here in this, what we're trying to cover here in this course, including the following. So what we're trying to do is you will learn mathematical methods for understanding data relationships and for system optimization. Apparently, that's why we call it mathematical modeling techniques, right? We're learning all these techniques that can be used to represent a complex system. And then you can learn some techniques such as how to use difference or system of differential equations or linear or nonlinear programming or algorithmic search method for optimization or integer programming and branch and bound and their uses. Branch and bound is one of the methodology that's heavily used to solve an integer program. And then you would learn how to use some of these modeling packages and then to solve these problems. And examples, we are trying to use some sort of actual application and try to give you a perspective on how these methodologies can be used in actual system. And then here we also listed this cost learning outcomes. You should be able to understand linear programming. You should be able to understand simplex method and how to apply simplex method on LP models. And then you should be able to formulate integer programming models, and you should be able to learn some commercial and optimization tools. This is really not a complete list. There are some other methods such as graph theories there, and also social network analysis. We all would touch upon. However, as you can imagine, it is a foundation course, and then we're trying to cover the breadth of different topics. So essentially, some of the topics are not as deep as it could be. So in many of the cases, for example, graph theory could be 1 or 2 semester courses, but here we wouldn't be able to cover the full spectrum of everything in graph theory. The idea is we introduce you to this concept and methodology, and then when you started need to use this, you would be able to dig much deeper and try to understand the methodology a lot better than it could be. Okay, and then of course we're trying to make sure that you would have good business understanding. You would have some sort of data programming skills. In the course, we're using R. I'm open to other language if you prefer, such as Python or anything that you prefer. But we're using R in this methodology, in this course. And actually, I don't teach a lot of R in the course at all. It's really just you are trying to use R to solve some of the problems, and then my solution of those problems are based on R. And then at the end, you would be able to have a good foundational math and statistics skills, and then you would be able to have a better understanding on the data, and then you would have a better understanding of the methodology as well, such as optimization and a little bit of social network analysis and graph analysis as well. And then you should be able, you will be presenting your final project through the course as well, so you would be able to practice on that front and have a final report ready. Hold on, give me 1 moment. Just one minute. Okay, here is the assignments and grading. You have to, you need to have participated in the online discussion forums, which is in the Blackboard system. It would count for 14% of the final grade. And then you have 7 assignments. They are equally weighted, which is around 56%. So roughly, it would be around 8% for each of the homework. And then course project would count for 30%. And then course project itself has multiple components. You can see here in later this section, I have some discussion. Proposal would be around 10%. And then your presentation slides around 10%, and then your presentation around 30%. At the end, your final report would be 50%. So as you can see here, all these 4 components would account for 30% of the course final grades, and then when they add them up, it's 100%. And then I want to mention here that is how many discussions that I'm expecting. You should have at least 1 substantial discussion every week. So 10 discussions are expected, including week 0, which is already, you have to finish it by end of week 1. Getting to know you, essentially you explain. I apologize, I forgot to share the screen actually. Okay, you can see my screen, right? Okay, let's just backtrack. This is a syllabus starting from, the course description and learning outcomes, and then learning outcomes addressed by the course, and then here is a grading that we're trying to cover. And then again, it's 14% of the participation, 56% of the assignments, and 30% of the project. And then 1 substantial discussion every week. You don't really need to start a new thread. You can comment on someone's topic, and then that would count. Of course, feel free to discuss more than just 1. And then here for the homework, you only need to, for each homework, you only need to finish 4. Here I said or 2. What I'm really saying is the last for the last week actually. That's because, but for the rest of them, it's really clear if you look at every week's delivery, then you would have a better idea. So essentially, we have 7 homeworks from homework 1 to 6. Each one you should finish 4, and then homework 7 you only need to finish 2. And then for homework 1, because it covers 2 weeks, this week and next week, then you should pick 2 from this week and 2 from next week, so that you have full problem to work with. And then I would only create 3 of the homework, but I'm going to provide all the solutions. You would be able to know what the solution it's more like a guideline. You look through, you try to understand. Of course, if you feel like something is not quite right, let me know, and then we can always discuss. And then, or you think solution is different from what you initially thought, and then we can discuss as well. Here is the general letter grid that we follow in a CUNY system. You probably are already very familiar with that. And then this is the required text. If you haven't ordered the textbook yet, you should definitely do that right away. And then I think it's very important for you to have the textbook so that you understand what it is, and then especially some of the key concepts you have to read through the textbook so you would understand them better. And then there is a supplemental text and material, which is from this section. We only use it for the integer program, but feel free to read them as well for some of the relevant topics. If you are really into the mathematics, you want to look at how some of the problems are solved and how some of the problems are formulated in a more extensive way in mathematics. Then the supplementary text would be definitely a good reference material. And then it happens that this supplementary text is a free text that you can just leverage directly. And you should use R. And of course, as I mentioned earlier, you can use any language that you prefer. Even though, one semester I found that when students keep using Excel, even at the 8th week, 10th week, I said, no, you cannot do that. At the beginning, you use Excel fine, but down the road, you're learning in this program, you can't, it's already the third course in the program. You cannot just finish the program using Excel. Not saying that Excel is not a good tool, but you're learning data science, you're learning data analytics, you have to have some sort of computational engine that you feel comfortable and you would be able to use in the future for your next job or for your new job or for your current position. You should be able to have some sort of computational language. It could be R, it could be Python, it could be MATLAB, which is less popular nowadays. So or it could be a SAS program, whatever that is. You should have something. And then feel free to send me emails. I will always try to answer you within like 48 hours time frame. And then here is the outline. I want to give you a high-level introduction on this outline. For week 1, so here, for example, the way that I lay it out, for example, this week is January 27th to February 4th. That's week 1. And then you have 2 components, and then it has specific chapters that you should be reviewing in those in the textbook. So if you don't have the textbook by 9 yet, you should definitely order it right away by the end of today. And then, hopefully by the end of the week, you have the textbook, and you can catch up the material. By end of next week, you will be able to finish homework 1 and submit the homework. And then the homework is always due by end of the week, which is Sunday 11:59 p.m. So you can think with that in mind, trying to finish them up. But the discussion should be finishing up by end of each week. For example, week 1, you should probably have 2 discussions. Week 0 discussion and week 1 discussion. Both of them are due by end of this week, and then again Sunday 11:59, and then you would submit them. So in other words, for first 2 weeks, you have 3 discussion that you should finish, and then you have homework 1 due by end of next week. And then, of course, we have all these topics that we're planning to cover, including simulation and some probabilistic modeling and the linear programming in week 6, with followed by week 7 graph theory and decision theory on week 8. and game theory on week 9, which is relevant to decision theory as well. And then we have homework due along the road. And then just want to remind you that we have game theory followed by modeling with differential equations. And then in between we have spring break as well. Just that note that homework 5 is due by end of week 11, and also project proposal is due by end of the week, which is a week 11. And then project proposal itself, I'm going to discuss in further detail shortly after this, and then you would understand what that is. And then we have homeworks 6 and 7 due right after, week 13 and week 15. We're going to cover some of the optimization methods such as nonlinear programming and graph models, and also integer program. And then basically we are done by week 15, and then you would have final project that you can present on week 16, which would be the project presentation slides due by end of the day on the class week 16, which would be main 14, 15, 16, I think. Yes, main 16, you should have your presentation slides due, and also you present your project on that day, and then but you could submit your report by end of the week, which would be the 20th. That's really the outline of the semester. And then remember that, make sure that you have you follow through some of this academic integrity, and make sure that you don't have plagiarism issues through the course. Just do your own work, try to finish the stuff by yourself. And then here, the last page of syllabus, I do have an explanation on the project that I kind of envision that you guys should do. You should select any phenomenon or real world or business problem of your choice and apply 2 mathematical modeling techniques to the problem, and present your findings clearly in your report. Compare them 2 methods if possible. So now you see that we discussed, we have probabilistic modeling, we have graph modeling, we have social network analysis, we have optimization, simulation, even a little bit regression, and then you can use 2 of these methods in that problem, try to compare them if possible. Of course, it's not mandatory. If you cannot compare, then that's fine, you don't compare. And then next, you can see here, for the team, you should have a team of 2. Of course, you feel free to do that by yourself. And then you can also even say, okay, I can have a team of 3 or 4. So in general here, I have give you some suggestion. Rule of thumb is, if you are working by yourself, please try one method that we discussed in class. Even though here I said use 2 methods if possible, but if you are doing just by yourself, 1 method should be sufficient. If you are a team of 2, you probably want to try 2 methods. If you're a team of 3 or more, maybe you still use 2 methods, but hopefully you have more depth of analysis involved. Okay, and then you have to form the team by end of week 11, and you have to submit the proposal by the end of week 11, and then it's 10% as I mentioned, and also the presentation slides 10%, presentation 30%, and final report 50%. And then your presentation should be around 5 to 10 minutes for each team, so that we will be able to cover them in just 1 session. And then your report should have all of these elements, not necessarily a complete list by any means, so you should at least minimal have some of these components. Analysis of the problem, the methodology used, details of the methodology, the findings from the project. Are they different from your initial expectation? If so, is there a explanation? And then potentially how you can improve for next step. And then here are the time that we are going to use. Oh, I think I actually didn't update this link. I would update this link and send updated PDF on the syllabus. But in the meet me section, I do have the updated link, so you can take a look. That's actually the like a high level explanation of the syllabus. Any questions so far? Okay, if no questions, we're going to just go ahead and start some of the material that we need to cover this week and next. Because it's the first, 2 weeks and the first session, actually these 2 weeks reading relatively light, so that you should be able to catch up very soon. And then in terms of material, it's not, in terms of depth of the material, it's not that difficult either. But starting from week 3 and 4, you would see that things getting a little bit more complicated, so it would be more involved, so that you should spend more time for the course. Okay, so hold on, let me pull up the slides. Okay, so now let's start the module 1 and module 2. So first of all, before you start, you should review the Appendix D, which is the brief review of integration techniques. So once you review this section, of course, if you already know, that would be ideal. If you don't know, you never studied this at all, then you should definitely review, because this section would be used in some other techniques like differential equations. You have to know how to do integration. And then make sure that you are comfortable with these math techniques, and then definitely ask questions if you have any, either through Blackboard or email, so that we are sure that you are up to speed in terms of understanding these topics. And then in this Appendix D, what it involves U substitution, integration by parts, and then rational functions and some partial fractions and distinct linear factors, repeated linear factors, and quadratic factor. So these are really some basics that you should know in college calculus. So by now, I assume that you should know. If you don't know, review the Appendix D, so that you are comfortable with these techniques. And then let's just quickly review what would be in chapter 1. So in chapter 1, we give you so the methodology is rather simple. It's just a modeling change. How can we use difference equation to model a change? How can we use difference equations to do approximation to get an approximation of the change? And then how can we come up with solutions to dynamic systems and systems of difference equations? And then followed by the homework. So here, this is a high-level introduction of what it is all about in terms of math modeling, right? So if you look at this diagram, starting from the top left-hand side, you know that real-world data, we can have real-world data. We start with the data, and then we simplify the data by using a model. We build a model on top of the data, so use some sort of simplification, some assumptions, and then we come up with a model, mathematical model, right? And then you, based on that model, run some sort of analysis, think through some deduction, and then you have some sort of mathematical conclusions on the bottom right, right? And then with the mathematical conclusions, it involves some sort of interpretation so that you can come up with predictions or explanations. And then on the other end, you can use real-world data to verify your predictions or explanations, whether they're correct, whether they make sense. How can we improve them? Okay, that's really the whole flow of the modeling process at a high level. Of course, this whole process is always iterative. It never be a one-way street. It will always be coming back to model again, think about the conclusion, and then look at whether it's verified. If not, do we need to adjust the assumption? What should we think about to further enhance the model? That's the whole process of the modeling. And then let's look at this is reasonably easy. So what is proportion? Y equal to k times x. Then we say that k is a constant, so that we say that y is proportional to x. And then this is just a definition of a proportion. And then how can we model change? Change is a future value equals to present value plus change. So that's easy, right? So that's why even though for the first chapter we call it modeling using difference equation, a difference equation essentially is future value minus present value equal to change. And then shortly we would be able to see. Sounds like a simple issue, but simple methodology, but it can be used to solve some problems. And then now, what if we have what if we can model the change using a sequence of equations, such as delta A0 equal to A1 minus A0, so that we know the difference between A1 and A0, and then we call it as delta A0, and so on and so forth, so that we know the n's first difference is delta A sub n equal to A sub n plus 1 minus A sub n. Now this is nothing but difference equations, and then we studied some of this already in high school, in college, right? So let's continue and see how this can be applied in solving some of the real world problems. So graphically, you see here, if we use x-axis being the n's, the numbers in terms of x observation, and then you can say that from time period n to n plus 1, which is a change of one time period, the value of a changes from a sub n to a sub n plus 1. So you can see that the y-axis difference is really the delta that we just discussed, and then the x-axis is the time period we discussed. Now there is an application. In simplified terms, mortgaging a home can be modeled using this equation. That is to say that b sub n plus 1 equal to b sub n plus 0.01 times bn minus this constant, and then b0 as an initial value, so that you would be able to calculate b1, b2, etc., etc. Hold on, actually give me 1 minute, I need to get some water, and then we can continue. Okay? Okay, if we continue, you can see that essentially this just the trajectory of the number of months, and then as time goes on, the loan value starting from 8,000 all the way to 0 paid off after 233, maybe 33 periods. So that's one way to look at this problem. Of course, in reality, because of the amortization and time value of money and interest, it's a little bit more complicated than this. But just from one view, you would be able to know how you would be able to use this difference equation to know the how to know the amount of outstanding loan value for a specific mortgage. And then how can we modeling change with difference equations, just with a set of difference equations instead of just one. Yeah, and then second section we discussed there was the change is some sort of function. How can we approximate that function? And then it could be the change could be discrete, it could be continuous. You can say that. And then you can say that the one on the left side is one potential application in the growth in East culture as time goes on, how this function change. And then you can see that equation form, in terms of the equation itself is really just a delta is a function of the previous 0.5 of the previous value. For the first one, right? For the second one, you can see that delta is a constant times a value, constant value minus the previous value times previous value. So the first function apparently on the left-hand side is just simply the delta is a function of previous value, but the second one, the delta is a function of quadratic function of the previous value, right? So that is some way you can think about this problem. And then question is, if you have an observation shows as a dark dots there on this chart, and then what type of model potentially you can build, a difference equation that we just discussed the previous page, using that equation that we had, delta p sub n is equal to 0.5 p sub n. And then what would be the potential prediction that you have, which is the hollow circles there compared with actual observations. So you should build a model that try to match the reality. Of course, in the computational mathematics, you already studied difference between a model and the potential possibility of overfitting. We're trying to avoid overfitting in any of the modeling exercise. We're trying to make sure that the model is sound, conclusion is sound, and without overfitting of the real data. So just pay attention to some of those aspects, and then we're going to discuss that in the course through the semester as well. And then in terms of how to solve a dynamic systems problem, but essentially this is really true for any of the modeling, right? You start with the data, look at the data, do some sort of analysis, and you look for a pattern, and then so that you kind of get a conjecture. You think, oh, it looks like A is causing B, or A and B have this relationship. And then you try to build that model to test the conjecture to see whether that makes sense. And then at the end, you conclude, oh, initially my conjecture is correct, and oh, my conjecture was not 100% correct, probably 80%, and then where did I miss? How can I further enhance my conjecture? What type of analysis or data I can further use to enhance the conclusion of the conjecture? or to prove the conjecture is correct. And then in terms of a continuation of what we discussed on the previous slides, then what if there's a linear dynamic system, which is saying that we're no longer modeling the difference from period to period, we're modeling the linear relationship between n sub 1 n plus 1 equal to r times a sub n, and then you would know that essentially a sub k is r powered by k because r is a constant times a0. A sub 0 is the initial value. And then for this type of linear dynamical system, how can we find the equilibrium value or the fixed point of the dynamic system? And then the solution is really that A is for this particular theorem too. If you look for this particular dynamic system, A sub n plus 1 equal to r times A sub n plus b, the equilibrium point or fixed point is really that A equal to b divided by 1 minus r. And then of course we know that if you know that if r and r equal to 1 and b equal to 0, then every number is a equilibrium value, meaning that this doesn't, meaning that it's basically constant, right? Meaning that b is 0, and then every time it doesn't change as time goes on, the value doesn't change. And then if you look at the theorem 3 here, the solution of this dynamic system is really this a k is powered by k times c plus b divided by 1 minus r for some constant k. It really depends on the initial condition. So that gives you a high-level idea of what is a linear system. And then how about nonlinear system? Nonlinear system is nothing but, current value is a function of previous value times previous value. You can see there is a sub n squared component in the system in this equation set, right? So later you would see that, okay, what is a linear programming, which means it doesn't have nonlinear component x powered by 1. And then for nonlinear programming, mathematical models optimization, it has nonlinear component, meaning that there is an x quadratic function, x powered by 2 in the system, or potentially x powered by 3, or x powered by 4, then it becomes nonlinear in the system. Okay, and then in this section, from page 37 to page 55, there are multiple examples on how you can use linear system or use the difference equations to solve some of these business problems. I think it's very interesting, especially that some of this analysis we actually need to go through from some other perspective later on in the differential equations, later on in some other methodology that we still use some of these examples as well. So definitely go through some of this so that you know how they can be applied. If you look at the last one, discrete epidemic models is by no means different from what we just took a quick look on the mortgage home. But how you apply this simple concept into the real world problem is really the key of this section, some of these case studies. So definitely go through them when you get a chance, when you get the textbook. And then, as I mentioned, this example we will be discussing much further detail using other methods later in the course. So that make sure you understand these examples first. If not, pay attention to sensitivity of initial. If not, definitely let me know if you have questions. And also make sure that you pay attention to sensitivities of initial condition, which is important in any of the modeling exercise. That is to say, the stability of the solution from the model. So you want to make sure that your solution is sound, your conclusion is correct, and then it doesn't suffer from the initial condition instability. So you want to make sure that the model is generating solid results. Okay, here is the homework. As I mentioned, for chapter 1, for example, this is the first week, but it's really not first week. It's not homework 1 due by end of this week, but you can pick 2 problems from this set, and then as a subset for homework 1. Homework 1 is really due by the end of second week. So first week you have 2 problems, second week you have 2 problems as well. So for homework 1, you should have 4 problems that you submit, but you can choose to work on this for maybe by the end of next week. So you don't really need to finish them up by this week, so that it's easier for you to make sure that it fits your schedule and you will be able to finish them on time. Okay, that is the first module. And for the second module, it's rather straightforward. It's actually don't have a lot of material that we need to cover. So let's continue with this. For second module, which is supposed to be something I should be reading next week, and then let's see what it involves. Continues with this mathematical models that we discussed, and then what it is all about, why we use mathematical models. And then it talks about how to model use proportionality, how to use geometric similarity to model. And we followed by section 2.4 and 2.5, followed by some examples in those 2 sections. So again, review those examples, which would be very interesting to read. Actually, the textbook, I think, did a good job on explaining the math concepts and then trying to explain in a way that it applies to real-world problems. And then here, I want to talk about here is, if you look at those 2, what's the difference? It's really in terms of real-world systems versus mathematical model. You can see that real-world system is observed behavior or a phenomena, and the mathematical world is the models you use to model it's some sort of mathematical operations or rules, and then at the end you should have mathematical conclusions. And then look at the left-hand side, the graph, a chart on the left-hand side versus the right-hand side. The key difference is really on the right side of those 2 charts. So let's look at it, and then what's the difference there? You see that in a real-world conclusion, you just use real-world behavior and try to do some sort of trials, do some experiment, and then you have a real-world problem. But on the other side, you can use real-world data to verify whether your conclusion is sound, as we just discussed earlier. But there's some subtle difference in the sense that what type of model we should be thinking about, and then whether should we just do experiment instead of doing some sort of math modeling. So look at here. From here, this perspective, if we have some sort of phenomena that of interest, you have 2 ways. One way would be think about mathematical representation, and then it would be a math model. And then it involves model construction and model selection. You could have multiple candidates of models, and then you potentially can come up with hopefully consistent conclusion, but different consistent conclusion, so that you have to make a decision on which model is telling the true story and whether it's doing its job, right? And then you have a different section. You have a different venue or route you can take, which would be replication of the real-world problem, and then more like experiment, right? And then here we have 2 ways. One is doing an experiment. Second way would be simulation, using computer to help you to simulate the whole process, so that that's another way that you can think of. So two ways: mathematical representation or replication of the behavior. And even in replication of the behavior, you could have experiment, you could have simulation. Now the question becomes which venue you should take, which route you should take. In what scenario you want a math model, in what scenario you want to go through simulation. So I would say that the rule of thumb is really that if the mathematic model is good enough to represent the real world, you probably want to try a math model. But sometimes, because we know any model, including math models, it would have all sorts of assumptions, right? And then in reality, that becomes whether the assumptions are correct, whether some of the assumptions are made using wise decision to make those assumptions. So, and then also model selection and model construction. It involves all sort of potential human error and potential risks involved. So that's from that perspective, if you cannot simplify the problem using a math model, then you can start thinking about experiment simulation because it's more expensive. And then let's look at the charts on the bottom. Let's look at flexibility first, which is on the rightmost hand. In terms of flexibility, real-world experiment is really low. It doesn't have a lot of ways. I do experiment, I cannot repeat it very easily. But if you have simulation, you can repeat it rather easily, and even with the math model, it's even much easier to rerun. And then, however, on the other end, in terms of cost, in the middle, you can say that experiment and real-world observations are much more is actually cost less compared to some other models. If you want to build a model, then you have it cost-wise, it's more expensive. And then in terms of fidelity, real-world observations apparently it's better. You always have real-world data, and then the model is less, because of assumption, it has less fidelity to the real world. Just because you have to make certain assumptions, you have to think through certain component, how would you be able to model the problem? So this is really a high-level view of all the potential possibilities that you can think of. That's why first chapter and second chapter more so as introduction for math modeling. And then here, you're not these steps shouldn't be very hard for you, in the sense that you start with trying to identify the problem, you make assumptions, and then what assumptions? Identify, classify the variables, determine interrelationship between the variables and submodels, and then solve the model, verify the model, and then the question becomes, does it address the problem? Does it make common sense? Test it with real-world data, and then implement the model, try to maintain the model. And then, it's an iterative process, and then you have this model construction. So from step 2 to step 5, it's always a back and forth process. It never be a simple one-way street. You would be able to solve the problem just through one direction. And then you have to try to simplify or try to refine the model. Simplify meaning that you have to make certain assumptions. You have to, as this list shows you, you have to restrict problem identification. You have to neglect some of the variables. You have to think about some variables may be simplified by certain relationship, and then you have to incorporate some assumptions into the model simplification stage. And then on the model refinement side, you have to expand the problem. You have to consider additional variables. Maybe instead of looking at the linear relationship, you should think about nonlinear relationships. You're trying to reduce the number of assumptions so that you make sure that your model is sufficiently enough to capture the reality that you're trying to model. So it's a combination of both. You have, on one end, you are trying to simplify the problem. On the other end, you want to refine your model so that you make sure your model is doing a good job representing the reality. Okay, and then now we can get into some simple examples such as proportionality y equal to k times x, and then a lot of the proportionalities model that you have learned previously, such as Hooke's law, Newton's law, Ohm's law, and all of this different physics phenomena that you have learned previously. And then we are going to learn how to fit a linear model, which is a linear regression, which is actually the next section that we're going to discuss, and then give you a high level on what that is, how we can fit that model. But in general, it's some simple concept here, right? And then in the example, as I mentioned, geometric similarity would be something in those chapter 2.4 and 2.5. You should definitely read them. Give you high level of these applications. And then these are the list of homework for next week. You can pick 2 of them from this list and combine with module 1, 2 homework together should be submitting homework 1 by end of next week. That's pretty much actually our plan in terms of contents. Wondering if you have any questions. In general, logistics wise, content wise. But one thing I really need to make sure that you guys should start ordering a book as soon as you can. If you think it's too expensive, you think about other options like Kindle book, and then or you can just buy the book and by the end of the semester you can try to sell it. Just another possibility. Really depends on your view of it. But at the end, you should definitely get a textbook as soon as you can. Okay. If you don't have any questions, I'll just stop here, and then I should be talking to you guys in 2 weeks. Oh, unfortunately, I just realized that one thing that is 2 weeks from today's Valentine's Day, and then potentially we may have to cancel that the live session. But I definitely want to make sure that I have something for you guys. You would be able to go through the contents yourself, and then we can continue. Definitely communicate through emails if you guys have any questions. Okay. Okay, if no questions, I'll just stop here and have a good night.